In this video, we move beyond summarizing a single set of data using statistics to summarizing bivariate data using statistics. Now, when I refer to bivariate data, I'm talking about working with two variables at the exact same time and identifying the relationship between those variables. So let's begin by looking at an example that illustrates the relationship between the size and selling price for a sample of homes in a Denver suburb. So we have the size of the homes in square feet in the first column, and then their corresponding sales price in thousands of dollars in the next column. If I take these data points and I plot them in the figure at the right, I get what I call a scatter plot. Let's observe some things about this scatter plot. Well, our x variable is size and our y variable is price. But you're going to see that I'm going to move beyond the language of x variable and y variable in this module, and instead I'll refer to things like size as the explanatory or the predictor variable, and I'll refer to things like price as the outcome or the response variable. Because when we look at a scatter plot like this, we can say things like size appears to explain or predict the outcome of price. And that's definitely true in this case. It looks like as the size goes up, so does the price. And this is exactly what you would call a positive association. I want you to also notice that the points seem to cluster around a line. Now obviously they don't fall on the exact same line, but given the fact that they kind of cluster around a line suggests that they have a linear trend. And so this relationship here between size and price is a positive linear relationship or a positive linear association. And that's one of the several types of associations that you'll see in this module. So you can see that some other ones that you might see are negative linear associations, and this is where as one variable increases, the other is actually decreasing. A weak linear relationship or a weak linear association it'd be kind of difficult to identify the trend, whether it be an upward trend or a downward trend. It almost looks like a cloud of points in a weak relationship. And then we have nonlinear relationships, positive and negative. But we're not going to be focusing on those nonlinear relationships in here. Right now, we're only interested in working with those relationships that are the linear ones, and we will summarize those linear relationships with things known as a least squares regression line and a correlation coefficient R. The least squares regression line is going to be the single line that best fits all of the data points, and I'll dig into that definition for the least squares regression line a little bit more in a minute. Correlation coefficient is a statistic that is going to capture the strength of a linear association. Now you should know that both least squares regression line and correlation coefficient are based upon some complicated formulas that we're not going to get into in this class, but we will be focused on interpreting what the least squares regression line and the correlation coefficient give us. Okay, so you should know this also. Correlation coefficients are going to be between -1 and 1. And if I have a relationship or an association that has a correlation coefficient that is close to 1 or close to -1, both of those would be very strong correlations. One would just be a positive correlation, and one would be a negative. And then if you have a very weak relationship or a weak association, then the R value, the correlation coefficient, would be closer to 0. So if we just take a glance back at some of these plots, the R value here in this one would be close to 1 because it was a positive linear association or positive linear trend, and it was a pretty strong association. Same thing here. If this is a pretty strong negative linear association, this R value would be close to -1. And then in this weak linear association, here is where you would have an R value that would be close to 0. So let's, in the context of our example, look at least squares regression line and correlation coefficient. And before we do that, and I tell you exactly how to do that in the calculator, I want you to look at this plot again. And I want to illustrate in this plot what the least squares regression line is. So you can imagine that if you just kind of estimate by hand what the line is that best fits a lot of these data points, you can imagine that there's a lot of lines that you could draw through here. And the reality of it is there is a single line that best fits our data points, at least according to the least squares definition. So the least squares definition is this. It says if you take the distance between the data points and the line, and you could look at the distance by just drawing these vertical line segments like I'm doing right here. If you take the distance between all of the data points and the line, and you square those distances, and you take the sum of all of those squared distances, the least squares regression line is the single line that has the smallest sum of those squared distances. That's why we call it the least squares line. Okay, so given that, let's pull the calculators out now and let's see if we can go through the process of finding correlation coefficient and the least squares regression line for our example. And so the very first thing that you have to do is, and you only have to do this one time in the entire course, we have to turn our diagnostic on. And this is just a tool in the calculator that allows us to get all of the things that we want when we do a least squares regression line. And like I said, you only have to do this one time. So to turn the diagnostic on, we are going to go into the catalog in the calculator. And the catalog can be found by pressing second and then 0. So if I press second 0, you can see that I get an alphabetized list of all of the tools in the calculator. So who knows, maybe this would be handy for you at some point if you can't locate a tool that you need in the calculator. But I press second 0, and then I'm going to press alpha x to the negative 1. That's going to take me straight to the D's. And let's scroll down to diagnostic on. It's just down here a little bit more. There it is. And I'm going to press enter, and then I'm going to press enter again, and it just says done. And that's all you need to know is it says done, because when you go in and calculate the least squares regression line, it's going to give you everything now that you need. If you're not getting everything that you need, then maybe somehow the diagnostic got turned off. Okay, so let's go and enter our data into stat and edit. And you can see that I've done that here. And here is my square footage, and then I've got the corresponding sales prices. Now I've detailed the steps that I'm going to be walking through. I've detailed those in the notes, and so you could follow along in the notes if you'd like, but hopefully this will make it pretty clear also just by walking through it in this video. So the next thing that you're going to do is you're going to say second y equals and go into that stat plot menu, press enter, and we have to turn the stat plot on. Recently, we've been working with things like histograms and box plots, and now we're going to select the very first picture, which is the scatter plot. So we select the scatter plot, and when you select that scatter plot, make sure that your X list is L1 and your Y list is L2, as long as that's where you put your square footage data and then the price data. Okay, now let's leave this menu the exact same way we left it in the past when we were looking at the other types of plots, and that's by pressing zoom and then going down to number 9, zoom stat. And there it is. There's the scatter plot that we've been already seeing here in this video and in the notes. And so now let's summarize this linear relationship with a line of best fit, and let's also get that correlation coefficient. And we can do that by going to stat, and then you go over to calc, and there are 2 lines of best fit. You can use number 4 or you can use number 8. And just to be consistent with connect, I'm going to choose number 8 right now. Now you should know that ax plus b or a plus bx are both forms for a line. And so you're not going to be wrong if you go with choice 4. But in this case, in choice 4, they're putting the slope in front of the x value and then adding the y-intercept. Whereas in number 8, they're giving you the y-intercept and then adding the slope times the x value. Remember, the slope is always the number in front of the x value. Okay, so I'm going to press number 8, and I have the calculator set up where I'm actually prompted for my x list, y list, etc. And so I entered the square footage data in list 1, so that's my x list. I entered the price data in list 2, that's my y list. Leave frequency list blank, but I do want you to go down to store regression equation, and we are in fact going to store the regression equation into the calculator. We're going to store the equation into y1, and here is how we're going to do it. We are going to press the variables button, or vars, and then we're going to, let's do that, let's say vars, Now let's go over to y vars, or y variables. Okay, and now let's press function. And then after we press function, we will press y1. So it's variables, y variables, function, y1, and it gets stored right next to stored regression equation. And the nice thing about this is it's going to take this long, complicated line of best fit. It's going to take that whole equation. It's not going to round it at all. It's going to put the exact calculation into y1 in the calculator. I'll show you here in just a second. So we hit calculate, and we get y equals a plus bx, and it tells us what the a value is, and it tells us what the b value is. Again, the a value is called the y-intercept, and the b value, the number that goes in front of x, is called the slope. And so I'm going to write this down. I'm going to write our equation down here as follows. Let's say that this is y is equal to 160.1939 plus 0.0992x. Or to give it a little bit more context, we have the price of a home is approximately equal to 160.1939 plus 0.0992 times the square footage of the home, the number of square feet. Okay, and there you go. You see that we also have an R value. We have that correlation coefficient of 0.9006, and that's if you're going to 4 decimal places. And that's kind of what we were expecting. We were expecting a pretty high R value, close to 1, because we had a strong positive correlation. Remember how I said we stored the regression equation into y equals? So look at that. It took the entire thing, wrote it in there for us, and now if we just press the graph button, it gives us that line and shows us how that line relates to all of the other points. And so now we can actually use this line to draw some conclusions. We can try to make some predictions, and we can try to do some other calculations related to the line. And I mentioned that here. I said some useful tools with regression lines include predicting average outcomes for a given value of the predictor variable and interpreting the slope. And so those are the two things that we'll do right now. The first one is, let's predict. We are going to predict the price of the home that is 3,000 square feet. So what I'm basically saying is, let's take 3,000 square feet, plug that into our model, and figure out what the model is suggesting the price of the home would be. But the nice thing is I don't have to go into this equation that I have written down here by hand. I can let my calculator do this calculation as well, because we have our equation stored into y equals. So what we're going to do is we are going to press second trace, and this is going to take us into the calc menu, and I want you to press number 1 on value. And when you hit enter at value, it'll prompt you for an x value. It'll say, okay, well, give us the x value, then we'll give you the value. And we want to know the price of the home that is predicted when the square footage is 3,000 square feet. So I plug in 3,000 and just press enter. And you can see that it goes to the model, or the line of regression. And you can see that the price of the home would be approximately 457,000. And if you're rounding to a couple decimal places, maybe 0.79 or something like that. So pay close attention to the rounding as usual when doing your homework. But this is what I call the predict question. When you have a model, you can always predict the outcome by plugging in any value of the predictor or the explanatory variable, just as we just did. Another common type of problem is what I call the differs problem. Now this differs question gets at a direct interpretation of slope. So let's look one more time at the equation that we came up with down here, and let's look at this number that we have in front of x, this 0.0992, and think about what it represents. And the way that I want you to think about what it represents, let's begin by considering plugging in a square feet into the equation again. And we could use the one that we just did, like 3,000. So if you plug 3,000 square feet into this equation, it's going to give you a price. Well, if I plugged in 3,001 square feet, it's also going to give you a price. But can you see that the only difference between 160 plus 0.0992 times 3,000 and 160 plus 0.0992 times 3,001 would quite literally be an additional 0.0992. That is exactly why we say that this number, the slope, refers to the change in this variable, or the change in our outcome variable, for a 1 unit change or 1 unit difference in our explanatory variable. And so a lot of times I encourage my students to even write the slope as the slope over 1 to emphasize the fact that this represents the change or the difference in the outcome variable for a 1 unit difference in the explanatory or the predictor variable. Now our question says, if two homes differ by 100 square feet, how much would you expect their prices to differ? Well, if we know that the prices differ 0.0992 for each 1 square foot, then we can just scale this up to figure out what the prices are going to differ by if the homes differ by 100 square feet. And so if for every square foot difference there's a 0.0992 difference in price, then for 100 square feet difference, it's going to be 0.0992 times 100 difference in price. So the way that you can approach this differs question is simply by taking the slope and multiplying it by the difference amount of the explanatory variable. And in this case, if we take 0.0992 multiplied by 100, then we get 9.92, and again, this is in thousands of dollars. So this is saying if you have two homes that differ by about 100 square feet, then their prices are going to differ by almost $10,000. Okay, so I'm going to go through another example just like this in the next video, and I'll probably go into a little bit more detail since that video will only focus on the example. So make sure to check that one out now. Thanks.